Okay, hello. My name is Stefan, and today we are going to debug the new ctfe system a little bit. And I've built nice new debugging facilities which will help us to track down our ABI issue that we are currently having. Now, let's see what's going on. We have a copy here, which is 0. Right here, and we can see in our system here that this thing is presumably an allocated temporary because it doesn't have a name. The other real variables in our system now have the name of the variable inside the disassembly, which is done by associating the address of a thing with a name, and yeah, this is how we do this. Of course, this can't track stuff where we create a temporary from something and use that. We could give this a name probably, but currently I don't know which name would be good here. So one thing I'm curious about is this here, where we assert 2 times that we have the result variable, and then we load from stack pointer 12, and I'm pretty sure stack pointer 12 should really be a variable. So something is wrong with the heap load 32 here, with the debug output of the heap load 32, because I am pretty sure that this should actually be result, because then this would load the base, and here we add the result to this temporary, add 4 to it to load the length. But yeah, something is wrong with the heap load here. So let me really quick check this in the printer. Whoops. And the printer is, of course, in the bytecode interpreter itself. Let's go to print instructions. There we go. This here allows us to get the name of a local outside of the stack map. And presumably this is not done on load, on heap load 32. And yes. So we can see this quite clearly, that instead of toString high here, what we really want to do is to get the local name. So we can just concatenate this with a stack map. Wrong. Local name. Is it capitalized? Yes. And then the stack map has the first parameter. And if it is null, we will return something with SP. And then the high shifted by 16, which should be the right offset here. And the same should be done on heap store. So This just replaces to local name, right? Yeah. That should be that. We could do this for load and store 64 as well. I mean, why not? In which case we would just say local name stack map. There we go. Now this should work. This says 1. Brace too much. And of course it didn't work. There's something wrong with the string. That's the problem when you work with such giant strings, but we already found what it is. So yes, this should work. And there is one white space too much. Let's see if we compile. We don't. We don't call the right function. It's 1688. We don't pass the stack map. Is that true? Yes. Now, we do pass the stack map, which should allow us to see the locals even there. And now we do see them even there. So let's go through this. This here allocates. This is the initialization of the of this results variable here, which is a slice. An array gets passed in. Is that true? I thought this thing should take a slice. Let me check. Oh, yeah, well, it can very well be that this T is the actual type to take 2 ints. This is very possible. So that would explain that. But we wanted to check test func putter, and I don't think that gets an array. Now, R here, this one, it's a slice. It's not an array. But if it does get treated as an array, this would of course completely explain why we have such problems, because arrays get treated very differently from from slices. Well, actually they don't, but they could be. There's still a problem with the printout of the left hand side value of heap store. Let me fix this. There we go. And there's one. Price too much. Now actually it's that this one should go here. And this one should only be a comma. And with that, that is fixed. I would like to run deformat over this, but deformat would probably make my formatting in other places worse. So I don't dare right now. This type being inferred as an array. This is very strange to me because arrays would have a fixed size. And I can't see this being an array. It has to be a slice. So maybe we did something wrong in our typing. So this here is the case when we have a static array. And in this case we create an array. In the other case we create a slice. So I really don't understand how this could happen. I have no idea. I mean, this obviously happens when we generate a parameter, because this is a parameter to a function. So here is what we do when we are processing parameters, which is this. And I guess I want to write out the variable declaration.type. So let's make a debug line. Let's and say we want to write out this type. And that should give me a clue. As to which type is being generated. This should be up here. There is a int array, function int, and I want to see the and I want to see the BC type that's been generated. So let's modify this line a bit there, and the BC type is type here, like that, and that should give me a better view into how my 2BC type does type this. And sure enough, those get all typed as slices. So I really wonder that the argument type is of type array, because we never created type array. I see what's going on. You see, this argument, right? It's an argument. So it's not based on the parameter type. It's created. Whoops. Is created here. See this? This is the argument, and this is indeed an array, right? Now, that's why the ABI of slices and arrays has to be the same, because you can pass arrays in where slices are. Well, or you could put in a costly conversion, but let's not do that. That's not nice. So, indeed, this is an array, because this is the argument type. This is not the parameter. So, result.length equals array.length. This is something that we do not necessarily see, but I could put it in a named local, in a named temporary that masquerades as a local, and then we could actually see what's going on here. And perhaps I should do that. So, see, right here, whenever we are modifying the length or something, we just end up with those temporaries here. And that doesn't help us. So loading heap.result. heap of results and all doesn't also really help us, because you basically you have to know the API for this, and I don't want you to have to know the API for this. So let me make a quick hack that will probably allow us to do what we need to do. Let's do this in the set base call. Base address pointer, and we can just or we could simply add a comment before we do that. Comment load space. This is set base actually. Set base. Right, and then we would at least see that this is what's going on. And I guess we have a set base in here. So let's see. We should have, because we are modifying a slice. There. Yeah, so we do set. Oh my, we have another bug in the printout of heap store. Let me fix the printout bug real quick, because they annoy the heck out of me. There we go. And thing is, of course, that when we're dealing with heaps, we do have this. We need to close this brace here. Okay. Now let's rebuild and let's see the new improved output. And hope that this annoys me less. Yes, now the brace is there. Just like it should be. And here as well. And here we store a particular value in E, right? And I can tell by this multiplication that's happening here, is that this is actually the index I. So somewhere here we need to we are loading I guess. So 144. There is the we're using result length to index. Really? Let me check the code. So we are using result length as in. Yes. This is this here, where we do indeed use result length to index this. Because the result length grow by 1 every time we have a hit, right? Then we set this, and then at the end this call here shrinks the filter result array, right? Wait, no. I create a new array. This is not how it should work. I should be able to simply slice the filter result. So I wonder why I didn't do that. Perhaps back when I did this, slicing wasn't up to the task, which can very well be. Yeah, in theory this should fix us up. Because this second... this result. This second copy was completely unnecessary. So here we can see that this does indeed give us the correct output. And let's make our filter function a little bit more interesting. Let's say it only let's through things that are divisible by 3. Right? This would be this. Yeah, and it says it can't convert to bool. Let's make a cast to convert it to bool, which basically means that everything that's divisible by 3, which will return, divisible by 3 will return 0. So this would give us everything that's not divisible by 3, which will give back a non-zero value. This doesn't seem to have worked at all. Could it be that we aren't evaluating the function? This seems very wrong to me. But why we can remove those superfluous braces, and I really wonder now. So if I have func return false, we shouldn't get anything. I suggest. I think. Yeah, now we shouldn't get anything. And I is called with the element itself out of the array. Right? This is the element out of the array. R is the return value. We assume that we can add. Then we call the... This is just This is bogus. We don't have to set it to true. I wonder why I did this back then. This should do fine. Actually, we wouldn't even need to... Well, let's do it like this. Well, it does fine with our system, and here we still have a problem. So we allocate a slice descriptor, set the result length to 0. If result is 0, we jump to 30. And result will not be 0 because we just set it. I wonder why we do this jump, though. I really wonder. So this loads the length from the array, I guess. So what do we do here? What is this jump 0 doing here? Because this would only happen if we didn't allocate. And where would we jump then? Yeah, this makes no sense. I guess this is something we do in case the allocation doesn't work. So this assert here should be an out pointer check. Or, yeah, I wonder where this assert is issued. And why? So let's see. You know what? I'm tired of this. I'm going to stop the recording, load this up, and we are going to continue this bug hunt a little bit later. So, 91 is the mem copy, that doesn't work. Before that, we store something in the result. And storing it directly means that this is the base. And then we multiply 60 by 4, which is the result of stack value 44. And now we have to track down where stack value 44 is set. And frankly, I can't see stack value for. Oh yeah, here stack value 44 is being set. Stack value 44 loads the length of result. And apparently result is 0. The length of result is 0. And this could very well be. So 28 should point to the length in the slice descriptor. And we load something from there. This looks very strange. Let me double check that we indeed have the length at the 4th offset. There we have a slice descriptor disk. And length is indeed at the 4th offset. Now let's change this up. And normally this shouldn't make any difference. The offsets will look a little bit different, but the rest should still work. And let's see. So now the adding 4 to the result is still here. Or is it? No. So first it loads the length of the result. And then it loads something from the first argument. So this loads the function pointer. No, it doesn't. This indexes So this loads the length from the array. So we should have a load here from 100, and it's 4. So this is the load of the length. Let's change back our ABI. Whoops. And now we should see a load from 104, and it should be 4 there. And if we change the length of the array we're working with to, let's say, 7, we will see that this will load 7 from there. See that? There's the 7. So far so good. Yeah, no, so we allocate 28 here. Where do we get the 28 from? Well, 7 times 4 is 28. Is it? Yeah. Times 3 is 21. Times 7 is 28. So this here allocates space for the result array. But at this point, the source array seems to be overridden. So this goes destination, which is valid. It's the our array, source, and size. The size is the source length times 4, and SP40 should be the source pointer. So somewhere here we must set something to 40. Because 40 is definitely temporary. There we set 48. But I cannot see us setting 40 to anything ever. There. 40 gets set by loading the base of the result. Which will be 0 because we never allocated it. So we found out what happens here. So again, what should be happening here is this line, result.length equals array.length, should allocate an array, but it doesn't. That's the whole problem here. that we do not have the dynamic allocation of an array, and therefore it stores all the information to nothing because there is no place to store it to. Now let's fix this. Now we know what's going on here. TTMD, ctfe, ctfe, right. Sign expression. There. This is an array length to array length assignment. Where we call expand to slice. If we do a comment here with the string representation of the expression, then we will very easily see that this is the line we're actually having here. If we ever visit this, that is. There. This is where this should happen. And why are we on an odd boundary now? Actually, that shouldn't happen if we leave comments. We should never get odd, it should always be kept even. Oh well. I don't care at the moment. So this said we load the base of the result. We get the base of the result. Oh, this loads the length. And the length should be 0. So in 88 is our dynamic allocation from 52 to 56, which should allocate 7 times 4. And we do this allocation here. After this allocation, we store the pointer into the base of the result, which got allocated just before. And the difference between those should be 28. But it's only 16. How come? Oh yes, because the slice descriptor itself here, it's only 16 byte long. So yeah, this is fine. So those numbers look actually correct. So I actually don't really know what's going on here. Yeah, so I need to think about this. This could take longer, so I'm going to stop the recording and let's keep it at what we have right now. So I hope you can see that seeing the actual variables inside the output does help, but it doesn't make it easy by any stretch of the imagination. So now let me stop the recording. How do I do that? Here. So almost an hour. So that